Hello everyone, I'm Chu Xinxiang. It is a great honor for me to give my presentation at Gecko 2024. My topic is differential evolution based on the lightweight surrogate for solving high-dimensional energy management problem. There are 5 sections in this presentation, include introduction, methodology, results, conclusion, and the final is the question and answer time. In modern power systems, the increasing emphasis on renewable energy sources like wind, solar power is transforming the energy landscape. However, integrating these variable uncertain resources poses challenges to traditional centralized energy grids. Therefore, the need for modern energy resources management frameworks to support smart grid development becomes urgent. But ERM optimization problems are often complex and high-dimensional, requiring advanced techniques. In the Gecko 2023 competition of evolutionary computation in energy domain, there is such a ERM problem. For a programmer, it is hard to make sense of the mathematical relationship inside the nested ERM framework. Therefore, the whole ERM framework is formulated as a black box function. As shown in the picture, only the input and the output can be observed. There are several typical characteristics in this black box function. Firstly, the dimensionality of the control vector reaches 13,680, which includes 24-hour information, in each hour of which the control variables cover active power, the state of generators, the charging and discharging information for electrical vehicles, etc. Meanwhile, to imitate the quick response in practical engineering, the total evaluation for the black box are limited to 5,000 times. According to the previous testing, the traditional evolutionary algorithms such as differential evolution and particle swarm optimization did not converge well with the limited evaluation times. This motivated us to find a method with cheap computational costs to provide rational search directions. According to our previous test comparison between differential evolution and Newton-Raphson, the two methods are used to solve the Rosenbrock benchmark respectively, and the initial population of DE are initialized around the coordinates -3 and -4. Which is also the starting point of the Newton-Raphson. According to the convergence trajectories printed on the surface and the contour figures, Newton-Raphson converges to the optimal in only several iterations, which is much faster than DE. So, we would like to construct a surrogate to provide similar search directions to enhance the conventional DE. With this background, we noticed the analog between the typical mutation formulas and the lower-order polynomial model, as shown in the 1 and the 2 areas. Suppose the decision space can be formulated as a hyperplane. We need to find one point and two nonlinear vectors. Because a hyperplane can be described with a point and two vectors lying on it. Some details can be found in number 3 and number 4 areas. According to definition, we utilize 3 sampling points, XR1, XR2, XR3, during the DE mutation stage to formulate the hyperplane model. Such a hyperplane model provides the mapping relationship between the vector x and the variable w1 and w2, as long as 3 distinct sampling points are given. So, the vector x is a dependent variable of the independent variables w1 and w2. Further, the fitness function fx can be transformed into a composite function of a variable w1 and w2. In order to obtain the coefficients beta 0, beta 1, and beta 2, we need 3 distinct sampling points. When w1 and w2 are set to 0, 0, 0, 1, 1, 0, 3 data pairs of the vector x and its fitness function value are connected in the table. According to which, we can calculate the estimated beta 0 hat, beta 1 hat, and beta 2 hat. However, at the current stage, only one equation with 2 variables is obtained. To obtain the Jacobian matrix, we need another one. So, to update one of the 3 sampling points, we can obtain the other one, a similar function. The details can be found in the number 5 and the number 6 areas. In the equation system, each equation represents an independent surrogate to approximate the black box function fx, so their intersection should be a more accurate approximation to the black box function. So, according to the equation system, we can obtain the Jacobian matrix and the solution of linear simultaneous equations by using Newton-Raphson method. Note, such surrogates are dynamic models during HDE mutation, which may be not accurate enough, but it can be enough to provide approximated rational directions to enhance the searching performance. Such a surrogate formula is completely compatible with the conventional mutation formula of DE. When we set a certain probability, say 50%, to replace the original mutation formula during DE mutation stage by using the proposed surrogate, promising performance appears in the corresponding simulations. According to the board font in the table, the proposed surrogate can reach 48,311, which is much better than the result of the rest. Besides, an additional set of benchmarks are adopted to validate the proposed surrogate, and the performance is also satisfied. The convergence speed can also be perceived by using contour figures. In the figures, the proposed surrogates can provide rational directions to accelerate the searching process. The proposed surrogate does not require additional computation cost than DE, and is completely compatible with the DE mutation formula. The most important is the proposed surrogate works efficiently and reliably. In our future works, we will concern with the situations with the boundary constraints. The main idea originates from my second PhD thesis. Thank you for listening.